All right, this unit, very much different from just derivatives, integrals, and application of things. Now we are just going to kind of deal with this situation more. What was this situation that we looked at is these improper integrals. And we're looking at this area under 1 over x from 1 and going on forever and ever and ever. So this function kept going on forever and ever and ever. And we're adding up all this area. And this too, for 1 over x squared, going forever and ever and ever on and on and on. And a lot of us assume that the answer to both of these, since we're continuing to add things up, is infinity. But, you know, it's not right. This is actually right for only one of these. It's almost like we've been dealing with infinities kind of all year. And we realized that if this wasn't from 1 to infinity, if this was from like 1 to 2, how do I find this area? Well, I am taking an infinite sum. So I'm adding things up, an infinite amount of things up to get this area from 1 to 2. And if you think, well, if I keep adding something, isn't this going to continue to grow? No, you can see this is a finite area. Okay, so this is just a number. But when I remove that thing here, and it's like, well, I'm going on forever and ever and ever, shouldn't that be infinity? Well, it turns out in this case, yes, it is. But in this case, no, this is wrong. Okay, we evaluated this, and we found that, you know, even though we're starting from 1 and going on forever and ever, that this actual area converges to a number. And we could say it approaches a number and it equals a number. Remember, this antiderivative is log absolute x. Change between 1 and infinity ends up giving us just infinity minus 0. This antiderivative is negative 1 over x. Find the change in this from 1 to infinity, and you get 0 plus 1, which is 1. The answer to this guy is 1. Okay? Similar situations, similar looking graphs, completely different answers. Okay? This is something that just deserves more attention from smart students like you guys. Okay? So we are going to look at whether infinite sums of things will converge to a number or diverge, which means, you know, maybe trend towards infinity, or maybe it just doesn't converge to a specific number. Okay? We are going to be talking about series of constants and whether they converge or diverge all units. Okay? Now, what is a series? It's just a sum of multiple numbers. Or terms. This is a finite series. We're only adding 5 things together. A sub 1 is just a number. All of these A's are just numbers. We denote all of these as like A sub n's. And I'm taking a sum of these A sub n's starting from the first n going to the 5th. Okay, this is summation notation. We'll be using a lot of summation notation this unit. And you just use this big Greek S for sum. This is where you're starting for. This variable needs to be the same as the variable being used in your summation formula. So, you know, if you have n equals 1 and you don't see n anywhere else, then that's just wouldn't make sense. You'd just be adding maybe the same thing every time. And this means n starts at 1, and this is where it ends, and goes to 5. And it's going to be going up by an integer, by a whole number. So you go A1, A2, A3, A4, A5. This is how you would list off this. Okay? Now, all finite series will have convergent sums. It's just going to be a finite sum. 5 numbers added together will just equal a number. But that's not what we're going to deal with. We're going to deal with these infinite series, where the terms go on forever and ever and ever, and we're adding them together. And we are going to figure out whether these series, these infinite sums, will converge to a specific number or just diverge towards infinity or towards just not a specific number. Here we would just list this off as the sum. Now notice this one is an a sub 0. That's our first term. Okay, what we will find is that n doesn't always start with 1. N sometimes starts with other numbers. In this case, we can say n starts from 0. And we're going to infinity of these a sub n's. But you know what? I don't want to start with 0. I want to start with 1. How can I write a sub n so that I get a0 first? Well, I can just subtract 1. And this is the same as this. Maybe I wanted to start at 2. Well, a sub n minus 2 gives us, starting with 2, a sub 0. And then I'd go to 3, give me a1. 4, a2. Okay, so little adjustments can be made easily based on whatever n you want to start with. We need to be comfortable writing summation notation using different n's, and by adjusting n by subtracting or adding 1. Okay, if I give you the summation notation, you should be able to list off the series here, 1 over 2n. Okay, n is starting from 1. So my first term will be n equals 1. I'll plug in 1 into this expression. I'd get 1 over 2 to the first, which is just 1/2, plus my next term, which would be n equals 2. Plug in 2 for n, and so on and so forth. Goes on forever and ever and ever. Now let's do this one. Now we will be seeing factorials a lot. We'll talk about the growth of factorials compared to the growth of other different types of functions in the future. Just to familiarize yourself with a factorial, it's just the number multiplied by the number minus 1 all the way till you get down to 1. So n factorial is n times n minus 1 times n minus 2 all the way till you have n minus 1 as the last term, which would give you 1. That doesn't have to make sense to you if this does. So things to note: 1 factorial is just 1, and 0 factorial is 1. Why is 0 factorial 1? Factorials are used for combinatorics, and like how many ways you can count things. Like how many ways can you select 5 different books off a shelf? Well, you got 5 ways to pick up one book, okay, because you have 5 choices. But then you have a book in your hand, so then you got 4 books to choose from, and you got 3 books to choose from, and then you got 2, and then you got your last book. So how many different ways can you choose 5 books in order? 5 times 4 times 3 times 2 times 1. Well, how many ways can you choose one book? Well, there's just one book, so there's only one way to choose one book. How many ways can you choose 0 books? Well, there's one way. There's no books. That's my choice. I have one choice, and that's I can't pick a book. That's the way I could say 0 factorial is 1. Okay? All right. So we can list off these terms. Now notice I'm starting from 0. And you plug in 0 for your first term. I know it's like your first term, but your first term is when n is 0 in this case. Okay? And it's okay. N doesn't always have to start with 1 to give us our first term. Our first term is n starts with 0. And I get negative 1 to the 0 plus 1. That's negative 1 over 0 factorial, which is negative 1. Plus my next term, n equals 1. So that's negative 1 squared over 1 factorial. That's plus a 1. And so on and so forth. Okay? Now, will these sums converge or diverge? That's the question. Okay? And your calculator can help you answer this. And I'd like us just to explore things with our calculator for now, but we're not using our calculator all unit. So just a heads up. Okay? So though our calculator can help us kind of get a better idea if things will converge or diverge, what we're going to have to learn is different ways to be able to tell whether or not these series are converging or diverging by learning different rules and by examining different types of series and comparing them to other different types of series. There's different ways to be able to answer this key question. The essential question of this unit is, will an infinite sum converge? Okay, and you could pull up the sum by going to math 0. So math 8 derivatives, math 9 integrals. What's next in the calculus curriculum? These sums. So math 0. And you can, start at 1. Now you're not going to be able to plug in infinity. Okay, calculator doesn't like that. It's going to work on forever. So you could plug in values and just start increasing, and you could say 1 over 2 to the n. That was great. Over 2 to the n. And your calculator can just start adding up 10 terms of the sequence, the series together. And you can see it's like, all right, 1 over 2 to the x, it's really, really close to 1. If I added 10 more terms, so the next 10, and add those terms, am I going to continue to increase so that I'm going to trend towards infinity, or am I going to get closer and closer to a specific value? And you can see we're getting closer and closer to a specific value. And if I typed in more terms, if I go to 50, it gets to a point where your calculator's like, you know what, I'm done approximating. I'll just tell you the answer. That's not the answer, though. Your calculator should be showing you, more 9s. And as it continues to add the next term, it's going to get closer to 1 and closer to 1. And it's never really going to get to 1. It would just get infinitely close to 1. It's going to approach 1. It's going to get so close to 1 that it's essentially 1, and we'd say it's equal to 1. Infinitely close to 1. Okay? So we can see that this actually converges. Our calculator helps. We can do it with the other one. Math. Good. Math 0. sum. Here I'm starting at 0. I'm going to infinity. I'm going to just start with 10. 10 even might be too much for this one. I got -1 to the, I want to put this in parentheses, n plus 1. This is just horrible. Divided by n factorial. Math, perb, probability, 4. Okay, so we get this -0.367. I'm going to increase the amount of terms that I have, see if we expand or get closer to a specific number. We're getting closer to, it seems like, a specific number. Go to 50. We don't want to put in too big of a number, or else our calculator will just like keep chugging away. Okay, same number. So we can see this probably will converge. It's not going to just keep adding values. Just like that area, that infinite bounded area ends up being a finite number. All right, but throw that calculator away. We're going to have to come up with that same conclusion that this converges a different way. We're going to have to come up with this conclusion that this converges some other way, using rules, by evaluating these series, by kind of understanding what a series characteristics needs to be so that it possibly converges or that it definitely diverges, and going from there, okay? But at least we kind of get the idea of things. All right. Here's a couple more, only this one I'm writing out as the sum of multiple terms. I'd like you to write the summation notation. What I like to do is start to kind of see some patterns that are emerging. You know, this is 1 over 1. This is 1 over 4, which I can write as 2 squared. This is 1 over 3 squared, 1 over 4 squared. After starting to see that, I can see, okay, I can write that as 1 over 1 squared. And let's say this is my first term, my second one, my third. That corresponds with 1, 2, 3. I say, okay, this is definitely the sum. And starting 1 going to infinity of 1 over n being squared. Okay, and if for right now, if we want to know if this converged or diverged, we just have to use our calculator and kind of evaluate. Another thing we could do, let's say I wanted to write it as n starts from 0. Don't always start things from numbers. We need to be comfortable with saying, well, if this is n is 0, how do I get 1 squared? Well, just take that n and add 1 and square it. Right? That makes sense because it'd be a 0, 0 turn into 1, 1 squared, boom. Okay, so we need to be careful and comfortable, not careful, comfortable with writing things out using different starting points. Let's see if you guys can figure this out. Write this using summation notation, using n equals 0 and n equals 1. Multiple different answers. Or different ways to get this. Now, multiple ways to get this alternating sign to occur. You can either have a number be negative to a power of n, or you can just include a -1 somewhere to a power of n. So if I'm starting from 0, I can have just -1 to n. I know -1 to the 0 is 1, and then -1 to the first is -1. -1 squared is positive, so that will alternate signs. I see in the denominator, if I start with n equals 0, that would be a 2 to the n. And I got 3 to the first, and 3 to the second, and 3 to the third. So if I start n at 0, how do I make this 3 to the first? 3 to the n plus 1. If you did not get that, well, try writing it with n starting from 1. It's important to be able to write it multiple ways, n starting from 0, n starting from 1. Okay, it's -1 to the n minus 1 or n plus 1. It actually does not matter if you do n plus 1 or n minus 1, as long as we go odd to even each time we change, with the first one being an even. And then 3 to the n, because we're starting with 1, 2 to the n minus 1 to start with 2 to the 0. Questions about that? Okay, need to be comfortable writing things using summation notation. All right, so one thing we could do to help us determine whether or not series converge or diverge without using our calculator is by looking at the partial sums of these series by hand. Put your phone away, Miss Noakes. Thank you. Partial sums are the sums of the finite series within this infinite series. So finite sums of the series, infinite series. We denote them as S sub n. Okay, and our first partial sum would just be our first term. Our second partial sum would just be the first term plus the second term. Our third partial sum would be our first plus our second plus our third. And if you think about it, the next partial sum is just the previous partial sum plus the next term. Something like that. Okay, and we don't have a calculator, but we can have a general idea of what's going on when I continue to add these numbers together by finding these partial sums by hand. And these are to help understand if we are converging or diverging. Okay, so in this case, S1, 1/2. S2, 1/2 plus 1/4. That's 2/4 plus 1/4, 3/4. S sub 3, well, 1/2 plus 1/4 plus 1/8, or 3/4 plus 1/8. That's 6/8 plus an 1/8, 7/8. S4, 7/8. There we are. 7/8 plus 1/16. Well, 7/8 is 14/16. Add another 16th, and I have 15/16. As we start to see these partial sums, and then let's just do one more. S sub 5 would be S sub 4 plus A5. S sub 4 is 15/16. And I'm adding 1/32. That's 30 seconds plus 1/32 is 31 30-seconds. As I can see, Mr. Nahal, each partial sum, as we keep going from S5 to S6 to S7 to S8 to S100 to S1000, those partial sums are getting closer to which value? 1. Which means we could probably answer this definitively right now just by analyzing these partial sums, that this sum equals 1. Just because we can see the pattern and we can make an assumption about the partial sums moving forward. And we can even write this as an expression of S sub n. This is n2 to the n. And this is 2 to the n minus 1. Okay, and we'll talk about what we can do with that expression for S sub n. Okay, now we can visualize series. It's sometimes very important to understand through the visualization what you are doing. And the way we do this is just with points on an XY plane. Now what we're going to do is we're going to visualize the terms that we're adding up. This is one way to look at the series, A sub n. And we're going to have the n's on the bottom. So this would be, my first, second, third, fourth term. And we'll start with 1/2 here, and then a fourth is a half of that, and then an eighth is a half of that, and then a 16th is a half of that. And you'll just put dots saying, I'm taking this value, and I'm going to add this value, and I'm going to add this value, and then I'll add this value, et cetera, et cetera. So this is just a way of like, okay, these are the values that I'm adding together. I notice that the values are getting smaller and smaller. They're approaching 0. So I'm adding less and less each time. Now the question is, am I adding, enough of a decrease so that my sum is not going to increase towards infinity? Which we will find is the case for some of these series when my values get smaller and smaller and smaller. You do it for things that don't approach 0. Here we have 2 to the n, 2, 4, 6, 8, 2, 4, 8, 16, 32. N equals 1, 2, 3, 4. N, I'm listing off the terms A sub n, 1, 2, 3, 4, 2, double that, 4, double that, 8, double that, 16. And I'm adding this, 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 this. Okay, so ways to visualize the terms you're adding. We also like to visualize our partial sum. So instead of A sub n being listed on the y-axis, I'm going to have S sub n. We're still going to have n on the x-axis. And we started with our first partial sum. being a half. The second partial sum was 3/4, right? It was 1/2 plus 1/4. The third partial sum was 7/8. The fourth partial sum was 15/16. Okay, so this is how we're listing off the partial sums. S sub n. We could do that with this guy. The partial sums, the first partial sum, 2. The second partial sum, 6, 2 plus 4. Third partial sum, 6 plus 8, 14. Fourth partial sum, 14 plus 16, 30. Stay with me, Mr. Noel. I believe. Don't you guys sleep over the weekends? Did you sleep in over the weekends? No? Gosh. Kids. All right, well, this brings us to how do we know if a series converges or diverges? We can look at, their partial sums. And we can say, well, if I look at the infinite partial sum, or the limit as n approaches infinity of our partial sum, if that approaches a value, then my series is going to converge. Now, a series diverges if we do not equal a value. It's not that we're going to approach infinity, okay? It's just that we won't approach a specific value. Well, as long as it's not approaching a value, we have a situation where it's not converging. So let me tell you an example of not approaching a value. This series, -1 plus 1 minus 1 plus 1 minus 1. That's a series. It goes on forever and ever and ever. I can look at the partial sums. The partial sum, the first partial sum is -1. Second partial sum, 0. Third partial sum, -1. Fourth partial sum, 0. As I go to infinity, am I going to be approaching a value? No. So this guy, we would say, is divergent, because the limit as n approaches infinities of its partial sums does not equal a value. Okay, so oscillating things.
Why is the top one?
Because it converges. Series will converge if the partial sums will approach a value. Let's look at the previous one. Now, the previous couple, yes, one did approach infinity. If you look at these partial sums, you can see these partial sums are going to continue to increase and increase and increase. You could say that this series is definitely divergent. Well, the previous one, we could see the partial sums get closer and closer and closer and closer to this value 1. This would be considered the limit as n approaches infinity of S sub n. It would look like a horizontal asymptote. But this horizontal asymptote, this k value, this is what this sum of this series is. Okay? It's what our S sub n's approach. Our partial sums are approaching 1. We'd say this sum, therefore, would be 1. And I would say that the limit as n approaches infinity of my partial sums, that's 1. And that equals the sum of my series.
The top one would be convergent to 0.
No.
The first one?
This top one converges to 1.
No, the very top one.
The very top one. This guy?
Yeah.
It's the same as the other guy. But what's the difference? No. The difference is what am I looking at? So this is very important. This is one way to visualize things, by looking at their terms. These are the terms that I'm adding together. Okay? I'm not saying, oh, when I add all these numbers together, we're going to approach 0. It just means my terms that I'm adding up are getting smaller and smaller and smaller and smaller. Okay, so the terms that I'm adding up are smaller and smaller and smaller. And when I add them up, we can see my sums are getting closer and closer and closer to 1. We'll say that it converges, this sum, this 1 over 2n converges, and it'll converge to 1. Not an easy answer to actually find out for a lot of the series that we will look at. A lot of the times on quizzes and for your tests, your answer will be yes or no. Yes, it converges, or no, it does not converge. You'll have to have some justification behind the yes or no answer. But there will be, for a lot of our series that we talk about, there will not be enough that we can do to be able to say yes, and this is the number that it converges to. We'll just be able to say, yeah, it converges. It'll approach a number, or it won't. All right, so moving on. Let's look at these 3 divergent series. I'm telling you for a fact, these series are divergent. Now, we can analyze their partial sums, sure. And it's obvious if you start adding up their partial sums that each partial sum is going to be increasing, okay? But let's just look at the terms. If you're just looking at the a sub n's, the terms, how can we tell just by looking at the terms that these 3 series will diverge? Discuss with your neighbors this. Mr. O'Keefe, is perfect. I'd like you to just repeat what you just said to the team. Like for this, the first one's obvious, right? 1 plus 2 plus 3 plus 4. I'm adding bigger and bigger numbers. So this is obviously going to be approaching infinity, okay? Because I keep adding bigger numbers. But these aren't increasing. These numbers are getting smaller. This one is increasing. But this one, these numbers are getting smaller and smaller and smaller. But explain why this one we know is not going to converge towards a number.
So it looks like the values that are being added are converging kind of to 2/3. So you're going to keep adding closer and closer to 2/3. And if you keep adding 2/3, you're just going to keep adding. It's not going to go to specific values.
Yes, the nth term, this nth term that I'm adding, this is not an SN, this is the terms that I'm using, the numbers that I'm adding, is approaching 2/3, which means I just keep adding 2/3, no matter how far I go out. What am I going to be adding? Essentially 2/3 every time. Well, when I keep adding 2/3, that's not going to converge towards a specific value. my partial sums are going to continue to tick up and up and up and up and up. Does that make sense? The only way that we can have a series converge is if my terms approach 0. Okay, we'll talk about this. Okay, so this is adding 2/3. This is just adding 1 every time. And if I keep adding a number, you're never going to converge to a number. So this is called the nth term test for divergence. That if your terms do not approach 0, you'll be continuously adding a number. Your partial sums will continue to increase. It will not be approaching a nice little horizontal asymptote. If the limit as n approaches infinity of a sub n does not equal 0, then the sum of a sub n diverges. Okay? If your terms do not increase to 0, we know we're adding stuff every single time, and we're not going to converge. Now you think, oh, great. So that means if my terms do trend to 0, then I must converge. No, not necessarily. The nth term test for convergence really isn't like a theorem or anything. It just says if the limit of your terms equals 0, you possibly converge. Okay, the most famous series that we will be able to show that it diverges after we do some analysis is this guy. Okay, and with your calculators really quickly, I just want to show you that this happens. Let's look at the sum n starting from 1 going to infinity of 1 over n. That's 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, plus a seventh, eighth. Those terms are all getting smaller, right? They're approaching 0, correct? I'll write it down for you. And you think, oh, okay, well, they're getting smaller, so they're approaching 0. This series must converge to something because I'm adding smaller and smaller things every single time. And I'll be adding 1,000th. Plus essentially 10,000th, and then 1,000,000th. Okay? But let's look. Yep, sometimes you break your calculator doing some of this work. If I start at 1 and let's say go to 10 of 1 over x. All right, 2.928. Okay, great. Let's go to 50. All right, 4.499. Maybe I'm getting closer to 5. Let's go to 100. All right, 5.18. Seems like we're slowing down, right? Let's go to 1,000. No, now we're at 7.48. If you keep adding numbers here, this will keep increasing. Okay? This is an example of a situation, and we'll look at it more in the future, where your terms may approach 0, but it's not going to converge. Okay? But for the easy ones, If your terms don't approach 0, you're not going to converge. I'd like to give you a couple examples that I forgot to fit into your notes. Fit them in on the margins or on the previous page, maybe in the margins. And the question is, does the series possibly converge? Or definitely diverge based on the nth term test? I'll give you a couple. All right? Answer these and discuss with your neighbor. Will the series possibly converge or definitely diverge? And I started them all at 0. It didn't have to be at 0. I could have started them. I don't want to actually start this one at 0. I want to start this one at 1. I can't find the log at 0. Good thing, man. I changed that. No, just kidding. Didn't make that much of a difference the way you're doing the problems. Okay. Go. PC or DD? I'll do the first one for you. I'm looking at the limit as n approaches infinity of the terms. The terms are n cubed over 2 to the n. I know 2 to the n is growing faster than n cubed, so this is approaching 0. So my terms that I'm adding together are getting smaller and smaller and smaller, so that's good. Doesn't mean the series definitely converges. It just means the series possibly converges, because the terms get smaller and smaller, approaching 0. Okay, answer the other 3. Discuss with a neighbor. Discuss with a neighbor. second one definitely diverges because I would just be continually adding a half, okay, as I looked at larger and larger n values. This third one definitely diverges. E to the n is, oh, never mind, sorry. This one possibly converges. E is like 2.7, okay? That is, the growth of e to the n is slower than the growth of pi to the n, okay? It's not that you can say this is like, this would approach e over pi. You don't cross off the n's in this case, okay? This limit would approach 0. It's kind of like comparing x squared and x cubed. You don't say that you would use the coefficients because x cubed grows faster than x squared. Here, pi to the n grows faster than e to the n. So this possibly converges. I don't know if it converges or not. It just possibly converges. This last one, this limit approaches infinity. I don't know what I was doing. I got the last two mixed up or something while I was doing them. Last one approaches infinity because log is the slowest growing function. E is one of the faster growing functions. So this definitely diverges. Okay? Cool. So at least we can look at that. Look at the terms. And as the terms go on into the future, if we add something other than something closer to 0, we definitely diverge. Fantastic. Sometimes they will give you not what your a sub n is, your nth term, but your nth partial sum, s sub n. If you are asked to find this, so what is the sum? For this, if that is given. Now, if you think about it in terms of the last 4 problems we did, and if you have this listed as your a sub n, you'd say, oh, it definitely diverges. The limit as n approaches infinity of your a sub n is 2/5. So that means you're adding 2/5 every single time. But that's not what this question is asking. That's not what the question is giving you. The question is giving you s sub n. All right, so answer this question. Kind of goes back to before we talked about the terms, that the sum is just equal to your limit as n approaches infinity of your partial sum. If you know an expression for your partial sum, you just find that, and in this case it equals 2/5. We found in a previous example an expression for the partial sum for 1/2 to the n. Where is that guy? Back here. Right here. We found an expression for the partial sum for 1/2 to the n. We found that it was 2 to the n minus 1/2 to the n. Well, if you look at the limit as this approaches infinity, you can rewrite this as 2 to the n times 2 to the negative first over 2 to the n. This simplifies to be 2 to the n over 2 to the n times 2. If I looked at that approaching infinity, that'd give me a half, which is not 1. So I think I made a mistake somewhere. Because this is not 2 to the n minus 1, it's 2 to the n minus 1. change this back. I made a mistake here. So that's 2 to the n minus 1 over 2 to the n. You look at the limit as n approaches infinity. This is going to approach 1 because this 1 is insignificant. And that's what we found using our calculators and looking at the partial sums. Okay? All right, so that's a good start on things. But it's not good because, like, all right, well, I know we possibly converge, but I want to now start answering things like, hey, this definitely converges. And we have definitely diverges, but we do not have definitely converges yet. There's no one set kind of way to figure out if things definitely converge. There are multiple techniques to help you discover if things converge, definitely or not. But what's going to be the way we go about these series and whether they definitely converge or not is by looking at specific types. Okay, and we're going to go into the specific type and whether it converges or diverges and how we know based on their characteristics of a geometric series, and then we're going to look at something called like a P-series, a very specific type of other type of series, then we're going to look at alternating series, and we're going to just start developing rules, and we're going to create kind of just like a rule box, a toolbox, where you're going to say, oh, this is this type of series. I know this series definitely converges if it has these characteristics, okay? So it's different than derivatives and integrals. It's different than like, oh, this is what we do. It's more of like more stuff to kind of memorize and have in your arsenal here, okay? The first type of series we're going to talk about definitely converging is a geometric series. This is a geometric series. Let's say n started at 0. We would list this as a plus a times r plus a times r squared plus a times r cubed, etc., etc., etc. Each term is multiplied by r to get the next term. R is called our common ratio. A is just some constant. We would say that the next term, a sub n plus 1, would be considered like the next term, divided by my previous term. That's my common ratio, that's r. If I take ar squared and divide it by ar, I get r. Okay, some examples. Here, n starts at 0, so I have 3 times plus 3 times 2/3 plus 3 times 2/3 squared, etc. This times 2/3 times 2/3 gives us the next term. Same one here. I'm not going to go into that one. Okay. Now, if I looked at these, all right, and I use the nth term test, can we say this possibly converges or definitely diverges? And the same thing for this one. Well, here I got the limit as n approaches infinity of 3 times 2/3 to the n. That's like 2 to the n over 3 to the n. Three to the n grows faster than 2 to the n. This is going to approach 0. So as of right now, we could say this possibly converges. It's really 3 to the n minus 1, but it's still going to grow faster than 2 to the n. Okay, this guy, nth term test. I look at the limit as n approaches infinity of 4/3 to the n. You can write it as 4 to the n over 3 to the n. This approaches infinity. So I'm just going to be adding bigger and bigger terms every single time. So this definitely diverges. Well, after the next little thing we'll talk about, we can actually say this definitely converges. Because a geometric series will converge if R, the absolute value of it, is less than 1. And, which can be shown with the nth term test, if R is greater than or equal to 1, the geometric series is going to diverge. And it's really the same as the nth term test. I don't know why I put it in quotes. Same as the nth term test. You could just show the same thing. Okay? So, now this guy, you will say, oh, R, which equals 2/3, is less than 1. This converges. And this guy, instead of saying, oh, by the nth term test, it diverges, we could just say, this diverges. It's a geometric series, and R is greater than 1. Now, unlike most of the other series we're going to look at, the geometric series sum actually is easily able to be found. So go back. The sum of a geometric series is just equal to its first term divided by 1 minus R. You want to know why it's that? Wait till next unit. For right now, you're just going to have to believe me.
Next unit?
Yeah, next unit, Mr. Minion. Okay, we're going to talk about Taylor series, and we're going to get to it. Okay, but trust me, you don't want to know why now. Okay, so just believe me there. So if I asked you, okay, it converges, but find its sum, you can say, okay, I can do that. N is 0. My first term is 3, because it's 3 times 2/3 of the 0. So my sum is 3, first term, 1 minus R. 3 times 1/3, 3 divided by 1/3 is 9. Go into your calculator, prove it to yourself. Go from n is 0 to 50 of 3 times 2/3 to the n. You're going to get a number close to 9 or exactly 9, depending on how big you plugged in. Now, the sum for this one does not equal 4/3 over 1 minus 4/3. This is a value. This gives you a number, but this is not the sum. This is bigger than 1. Whoops. This is bigger than 1, so this diverges. This is wrong. Okay? If your series diverges, don't try to find its sum. Okay. Now, some it's not obvious to see the series, that it's a geometric series. Sometimes we'll have to rewrite things. I can write that as 1/2 to the n. I could rewrite this as e to the n times e to the first over pi to the n. Well, that can be written as e over pi to the n times e. Now, all of a sudden, I can see we have a geometric series. This r, less than 1, we converge. The sum is my first term. Well, n starts from 2 in this case. So starting from 2, I have 1/4 over 1 minus r. 1/4 divided by 1/2 gives us actually 1/2. This guy, n is starting from 1, unfortunately. Let's start it from 0 for fun, because I can write its sum is my first term. My first term, when n is 0, is e over 1 minus e over pi. And I would just leave it at that. Okay. Same thing with these. You just rewrite it using exponent rules, go from there. This is the type of question you may see. Okay, consider this series. Well, you're given what the first term of the series is, and they gave you what R is. Remember, the next term divided by the previous one, that's R. So if you want to find the sum of this series, in this case, it's our first term over 1 minus R. That's 5 over 2/3, so that's 15 halves. This guy, not giving you summation notation, but instead you kind of can notice that we're multiplying by -1/2 to get the next term. Because you see that, you realize, oh, this is a geometric series. We know that R is -1/2. My first term is 36. I can find my sum. It's 36 divided by 3 halves. That's 36 times 2/3. So that's 12 times 2, which is 24. Fantastic. The last type of question that you will see is finding the x's to make sure that the geometric series converges. So it says find the x value such that the series converges. Well, we know that the absolute value of R has to be less than 1. We can start with this. We can either solve this absolute value, understanding that the positive and the negative of the x over 4 has to be less than 1. Well, that gives you this equation. X over 4 has to be bigger than -1, but less than 1. And then that's how we can get the answer that x is between -4 and 4. I'll do the rest of the examples on the lesson. Homework's out of the book. Thank you. All right, so just getting rid of the absolute value, solving this, adding 3 to both sides. We see x has to be between 5 and 1. Okay. The next one, we would rewrite x minus 4 to the n. This is 5 to the n times 5. So that's x minus 4 over 5 to the n times 1/5. So I would create the r has to be less than 1. The absolute value of r has to be less than 1. And you can do the plus or minus if you'd like right away. You can actually multiply by 5 and then do the plus or minus if you'd like. It's up to you. Might be less work if you multiply by the 5 first. Do not add or subtract, though, with that absolute value. That's not going to work out well. X minus 4 is less than 5. X minus 4 is greater than negative 5. Add 4. X is less than 9, but greater than negative 1. Okay? Going back to the two problems we skipped. Does this converge or diverge, and what's their sum? I can tell that they converge already. I can rewrite it as negative 2 over 5 to the n times 1/5. The 1/5 is important. This is 5 to the n times 5. Okay. So it converges. What is its sum? Well, n starts with 0. So if I plug in 0, my first term is 1/5. 1 minus negative 2/5. That's 7/5. 7/5 divided into 1/5. So it's times 5/7. So it's 1/7. Okay. And then this guy, this is 5 to the n times 5 to the negative first. That's important to write that out so we get that first term. This is 6 to the n times 6. So that's really 5/6 to the n times 1/30th. The 5 comes to the bottom. 6 times 5 is the 30th. So this definitely converges because r is less than 1. The sum is we start this from 0. 1/30th over 1 minus r. That's 1/30th divided by 1/6. 1/6. So 6 over 30 is 1 over 5. All right, that's it. Intro to series and geometric series.